Okay, and now in this video we're going to be working with some the power of a point theorem. Okay, so it's problem one just says find zy in the diagram. So I'm looking at this and well zy isn't labeled, so I'm going to create the line segment. Okay, extended a little past. But now my first question is, well, if I'm being asked to find this distance, I'm going to call it A. I need to determine, well, I'm looking at this and I think I know what's going to happen. I'm probably going to say that this is 4, but I want to be able to justify it. Why is this side length B 4? So I see that 3 is 3 to 6 and 3 to 6, so that's a ratio of 2, and 2 to b, so that's probably 4, but let's justify it. Let's prove that that's the case. So if I construct triangles here, why are these two triangles congruent? Well, okay, I have vertical angles here. That's fair enough. But why are they congruent? And think back to the proof. The proof for the case where they meet inside. The reason is because, okay, well, I have vertical angles, but look at arc XY. Arc XY has an inscribed angle of XZY, but it also has an inscribed angle of XWY. So that means that these two angles are congruent as well. Okay, and therefore I have similar triangles with ratio 2, so with ratio 2 that tells me that if this is 2, this is going to be 4. And then to determine A, I can just use the Pythagorean Theorem, and so A is going to equal, zy, which is equal to A, is going to equal the square root of 16 plus 36, so 4 squared plus 6 squared, and so then this is going to be the square root of 52, or 2 square root of 13. Now, the other way that you can do this using the power of the point theorem more directly is you can say that, well, to find B, we can say that 2 over 4. Okay, so again, the ratio of the short part of the chord to the long part of the chord is going to, let me change that again. The ratio of 2 to B is going to equal 3 to 6, and then we can go ahead and solve and get B is equal to 4. 3b is equal to 12, divided by 3, you get 4. Okay, and then you could use the power of the point theorem similarly in this one. Now, this one wasn't such a great example of power of the point, but you could still use it. And now this one is a little bit more interesting. So it says points R and M trisect the line PS. So trisect means that this is congruent to this is congruent to this. Okay, and again, this diagram isn't exactly to scale, so go with what the prompt says. And then point U is the midpoint of PQ. So this length is congruent to this length. Okay, we also know that TM is equal to 2, and MQ is equal to 8. And then it says find the length of PU. So this is my unknown value. I'm going to call it K. So this is K, this is K, and I'm going to call these trisected components N. Okay, so now let's try to use the power of the point theorem. Specifically, I'm going to start with the values that I have, the numbers that I have, and the numbers that I have are 8 and 2. Well, what angles could I do, or what could I use the power of the point theorem in with these two numbers? Well, power of the point theorem, let's see, this is a point that meets inside the triangle, or inside the circle rather. So I can say that 2 times 8 is going to equal, that's the length of one chord again, split at this point of intersection, should equal n times n. Okay, so 16 is equal to n squared, and therefore n is equal to only positive 4. Negative 4, we can't have a negative distance. So n is equal to 4. Okay, so that's helpful. Okay, now remember, my ultimate goal is to determine the value of k. So what am I going to do? Power of the point theorem. Again, I'm going to set up, again, PR. So maybe I'll say, try that again. PR is equal to PS. No, try that again. Third time around is a charm. Okay, PR times now PS. So the product of that should be equal to PU times PQ. Okay, well, PR I know to be 4, PS is 12, PU is K, and PQ, sorry, is 2K. So simplifying here, 48 is equal to 2K squared, 24 is equal to K, and then therefore K is going to be equal to 2 root 6. So that means that PU is equal to 2 root 6. Okay, this problem was rather interesting in the fact that it made you use power of the point theorem both in the case of an intersection inside of a circle, and the point of intersection is outside of the circle. Okay, so again, just some quick examples of the power of the point theorem.